Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video describes the procedure for conducting hypothesis testing and constructing confidence interval estimates for two paired population mean values using both the old school approach and StatCrunch. Let's get started. Start off with, we need to talk a little bit about good experimental design, because in the previous mini lectures we've been looking at hypothesis testing and confidence intervals for independent samples, and now we want to look at how do we do the same thing for dependent samples. When designing an experiment, the question often arises, is it better to use an independent or dependent sample? And the answer is simply, we want to use a dependent sample that has paired data because it's generally better than using two independent samples. The reason for this is because matched pairs reduce the extraneous variation. So because you've got a link between a unique data point in each individual sample, it's that relationship that minimizes the variation between the two samples as a whole. Whereas with independent samples, you've got no real relationship between individual data points in each of the samples, and so therefore you could have any sort of relationship between any two data points, and that leaves more room for more variation. Of course, the more variation you have in your data set, the more likely it is that you're not going to be able to have any sort of relationship between them, and that's where the dependent samples actually have an advantage, because you do have a relationship between, unique data points, and so therefore that relationship is going to tether the amount that any one data point can actually vary from another. So how do we actually perform the hypothesis testing and build our confidence intervals for paired data? Well, first, of course, we have some requirements to meet because our methodology is based on certain assumptions. The first is that the sample data are dependent. Second, we're assuming that the samples are simple random samples. And third, we either have a large enough data set so we can apply central limit theorem, or we have a fairly normalized distribution for each of our respective populations. Once we have that, then we're all set. Now, there's some special notation that we look at when we're working with matching pairs. Okay, the first is a lowercase letter d, which we use to symbolize the individual difference between the two values of a single matched pair. So you're looking at, say, just off the top of my head, the weights of husbands and wives. So you've got the weight of the husband and the weight of the wife, and the difference between those two would be between a husband and a wife who are married together. That's going to be the D. And so for each of the pairs, there's going to be a different value for D. Then if you take the mean value of all those differences, then you get mu sub D. D bar is then going to be the mean value for the difference for the paired sample data. So mu D is the difference for the population. D bar is the mean value for those differences of an individual sample. Of course, S sub D is going to be the standard deviation for the differences for the paired sample. And then N is going to be the number of pairs of sample data. It's essentially the sample size as we've seen before. To test a claim, we're going to use the same conventions that we've always used with hypothesis testing. But notice our test statistic is slightly different. So here's our test statistic, d bar minus mu sub d over the fraction s sub d over the square root of n. So slightly different test statistic using those variables that are specific to paired data. Okay, notice that this mu sub d is the difference of the mean of the differences between sample values, and not the difference of the means of the samples or the populations. So very different. Okay, you're not taking the mean values for each of the groupings and then taking the difference of the means. You're taking the differences of individual data points in each of the groupings and then taking the mean of those differences. As always, we're going to look at p-values, critical values, just like we've done before. Constructing confidence intervals, we can do that as well. We have a general form that you see here, d bar minus our margin of error, d bar plus our margin of error, where our margin of error is the calculated according to the equation that you see here. So for most of the assignment problems, you're going to want to use StatCrunch, and there's a single option StatCrunch that can give you most of what you need. Just go to Stat, T-Stats Paired. Now, one of the things you notice about this series of menu options is that there's no option for with data or with summary. And the reason for that is that when you get to the options window, there's only one option, okay? The way StatCrunch was coded, it assumes that you have data that you want to test about claims about the means of paired populations, okay? So there's no with summary option that you can select. It assumes that you have actual data. So if you don't have actual data, then you're not going to be using, a paired data analysis in StatCrunch. So once you get to your options window, go ahead and select the columns where your data is located, and make sure you adjust your sign down here at the bottom for your alternative hypothesis. Typically, you're going to leave the 0 value here for your claimed value, and then away you go. And then in your results window, you're going to read off your test statistic and p-value, just as you always done. For confidence intervals, you can do the same thing as StatCrunch. Get to that same options window, going to Stat, T-Stats Paired, and then you're going to click the radio button down below for confidence interval. Typically, your confidence interval, again, is going to be 1 minus 2 alpha. There are some exceptions to that, though. First, if your claim doesn't match your alternative hypothesis, okay, so then you're going to revert back to your confidence level being 1 minus 1 alpha, not 2 alpha. The other exception is that once in a while you find a problem that specifies a specific confidence level. And if you have that specification in your problem statement, just use what you're told to use. Typically, though, that's not what you're going to see. Typically, you'll see, say, something like construct the appropriate confidence interval. And you have to figure out, am I going to use 1 minus 2 alpha or 1 minus alpha? And typically, you'll use 1 minus 2 alpha for the two samples, two populations, unless, of course, your claim doesn't match your alternative hypothesis, in which case you revert back to the 1 minus alpha. And then when you get your results window, your upper and lower limits, you read them right off the results table, just as you've always done. That brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.